Hello, everyone. Welcome to another lecture of your embedded systems. And today we are going to learn about another serial communication protocols, which is known as SPI. SPI stands for Serial Peripheral Interface. As you can see here in SPI, you have a master device and a number of slaves, depending upon the pins available on the master. So we can discuss more in detail in the just in a minute about this communication protocols. So it is a single master and multiple slave communication protocol. All right, so serial peripheral interface, also known as SPI, is the most widely used serial communication method that can be used to establish a communication between peripheral ICs such as ADC, DAC, DAC means for digital analog converters, shift registers, SRAMs, and other type of sensors, which can be easily embedded into a microcontroller system. So this protocol is synchronous, which means it needs to have a clock pulses, and it is full duplex, master-slave based interference. Full duplex means you can receive and transmit the data in the same time. So the data from the main, we also call it as master, or the subnode is known as a slave. So we have the master, which is main, and subnode is slave. So the data from the master to slave or slave to master is synchronized on the rising or falling edge of the clock. So clock is like a square wave pulse, which is generated to synchronize the data transmission. So either rising edge of the clock or either in the falling edge of the clock, the data is synchronized. And both main and subnode can transmit data at the same time. So SPI interference can be either 3-wire or 4-wire. The 4-wire is the most popular method, and I will discuss one simple example at the later of this lecture. So SPI devices support much higher clock frequencies compared to I2C, which means like we know like I2C is for communication between 100 kilobits per second to 400, but SPI support in the megahertz up to megahertz range. So the clock rate that you should use in a particular peripheral should be decided based on the manufacturer's specification of the particular device. So in that case, you have to refer the datasheet specifications. Right, so this is a 4-wire SPI interface. You can see like this is the master or the main. This is the subnode or the slave. So which has 4 wires to be connected. Apart from that, like you need to have a common ground between these 2 devices. So clock is there could be several names of clock, like S clock or SPI CLK or any other thing. If you see these kind of notations, remember like that is the clock generator between the master and the slave. Chip select, CS bar is the chip select, so which is used to select this subnode, which means like initially there's no communication. If you want to select this particular subnode, you have to set this line to low, and you can select this subnode. And MOSI is the master out slave with, which means the master sends the data to the slave from this line. And MISO is the master in slave out, which means the slave send the data to the master from this line. So as I mentioned, SPI could have multiple slave configurations. So in that case, your main or the master needs to have multiple slave selection bits. So here there are 3 slaves and 3 chip select pins like this one. Subnode 1 has one chip select, which is connected to the one pin of the master, and this subnode is connected to this pin of the master. Likewise, the third one is connected to this C3 bar. And this clock, OSI and MISO are common for both all 3 devices. And so if you want to make a communication between particular slave, for example, this one, you have to set the CS bar to logic low. Then you can start the communication while keeping other CS bar lines to logical high, which means they are disabled, and you can make a communication one at a time. So if you want to initiate communication between this guy, so you have to select this guy and disable these two. If you want to make a communication with this guy, disable these two and select this one. Likewise, while sharing the same data lines and clock lines, you can make a communication between all these slaves one at a time. So SPI has 2 different configurations. The most commonly used one is regular SPI mode. So in regular SPI mode, individual chip select for each slave is required from the master. So sometimes it is SS, sometimes it is CS bar. So let's assume this is CS bar chip select. So you have to initially this line is at logic high. If you want to select a particular chip, you have to pull this line down, which is connected to the slave. Then so you can start the clock pulses, and then you can send the data and you can receive the data. So here you can see like there are several bits in the slave in or master out. So these are the logic zeros. So this could be one clock period, and this is another clock period. Likewise, there could be several clock periods. So based on the clock periods, so the data can be ones or zeros. And here you can see the data out could be from as bytes, or sometimes they could be words, or sometimes 12 bits. So the data will send out by the slave either in rising edge or falling edge, depending upon the specification of the device that you are using. Right. So basically, what you need to understand is if you want to select a particular slave, you have to pull this particular line to low on the selected slave. That's what it is done here. And you have to generate clock pulses, and each clock pulses you have to send the data out from the master. And once the master slave understand whatever the instruction, then it will start sending the data back from the slave to the master. So SPI has different modes, like 4 modes are available, modes 0, 1, 2, 3. Also, they are called as mode 0, 0, 0, 1, 1, 0, or double 1. So the difference is they are like clock polarity and clock phase. Clock polarity is the clock when the CS bar is at the idle state, which means you can see here in the previous case, the clock is at logic low when the chip select is at logic high. So see, this could be either these 2 forms, right? So we have that CS bar, so which is initially at high. If you want to select, you have to pull that line down, and then we have the clock CLK. So it could be, this is the point where you start the communication. So if your clock generator, like it will generate some clock pulses. if it is initially at logic low, it could be either SPI mode 0 or 1, right? If it is at logic high, that could be SPI mode 2 or 3, right? That is the polarity. And the clock phase is the where you sample the data, right? So in mode, so the clock polarity is selected by CPOL, right? Clock polarity bit. So if it is 0, which means like initial voltage of the clock pin will be 0. And if it is high, the initial voltage will be high while C is set high, which means this is the ideal state when there's no communication happening. Now, in this point, the communication starts and the clock will be generated, but we are interested in this period. And clock phase bit is, if it is 0, the data sampled on rising edge. So there's another data pin as well, right? Let's say like a slave out, master in, slave out, right? So the master will start like slave can send data. Initially it is low and slave can send the data. And so this is 1, this is a 0, and likewise. But the master will sample the data on the rising edge of the clock, right? This is a rising edge. This is a rising edge. So in this point, whatever the data on this bus will be taken as it is a 1, right? And the data will be shifted out on the falling edge, right? So the slave will send the data on the falling edge. So we will discuss them in detail in the next slide. But remember, like, so the data sampling and sending will be done, and it is known as the clock phase. Clock polarity is the voltage state of the clock generator before starting of the communication. Now we can check example, which is from the MCP 3204, which is an analog to digital converter. And so it supports multiple SPI modes. So they say this chip says like they support the mode 00, which means the one that we have just discussed, which is SPI mode 0. Clock phase and the clock polarity and the phase both are 0. So these are the settings. So the clock polarity is initially at logic low. So this is a chip select pin. Initially it should be logic high. If you want to initiate the communication, you have to pull this line low. And the clock voltage is 0, which means like a logic low. So this is mode 00. We know like it should be logic 0, 0, right? So this is that one. So it is true. And data sampled. Let's think about clock phase, right? So this is the clock pulses starting from 1, 2, 3, and like that. So this is a one single clock, right? So it should start from here and end here. So this is a one period of your clock. And this is the second one, likewise, right? And rising edge is this one, right? This is start and it is rising, and falling edge is this one. It is falling to 0. Now, you can see now this one labeled, it has all these are rising edges, right? So MCU latches the data or sample the data on the rising edge of the clock. So these are the rising edge, you can see. So the data will be whatever the data is taken, sent from the master will be done at the middle of this point, right? And also whatever the data coming from the slave, so this is null bit is 0, and this could be either this. If you see something like ups and downs, which means either this could be a 1 or either it could be a 0, depending on the data available, right? So that's why they are showing like that. This is a 0 bit because it is 0, and this could be either 1 or this could be 0, depending upon the data available. And as you can see here, now this one, bit 11, it is right at the middle of this rising edge, right? So your microcontroller will check this voltage, whether it is a high or low, and count it as a bit, right? If it is high, it is taken it as 1. If it is 0, it is taken as 0. It is done at the rising edge of that signal. So the data sampled on rising edge, and the data shifted out on the falling edge. So if you take a look at the this one, so master send the data to the slave. So this is a falling edge, right? So the start bit is starting at the falling edge and is sent within the falling edge, right? Likewise, and even in the slave also, this is a falling edge. So these are the falling edges. So the data will be sent out from the slave this point, and it takes the entire clock from here to here to send this bit, right? So that is why there could be different types of different modes of SPI, but that is entirely depending upon the peripheral that you are going to use, right? It could be either you can find any communication. It could be either mode 0, 1, 2, 3, these 4 modes, right? So that is what we call as the SPI normal mode. And with the example, regular SPI mode, we have discussed the different modes. And the thing is, like when you're having multiple slaves in regular SPI mode, you need to have, the master needs to have different pins for chip select, right? Now here, like these data lines are shared between all the slaves, but when you're having 3 slaves, you need to have 3 chip select pins dedicated by the master, right? So if the number increases, the number of slave increases, you need to have more and more digital output pins from the master. So that is a drawback of the regular SPI mode. So you have to dedicate more and more digital output pins when you have more and more slaves. To overcome that limitation, so the daisy chain SPI mode has been introduced. So that is also applied in many Marcus peripherals. So in that mode, so you need to have only single chip select pin. So you need, so when there are 3 slaves, still you need to have a single chip select pin. So the number of slaves could be increased, but you only have single chip select bit. But now these data lines are not shared in the same manner as the regular SPI mode. The clock is common for all slaves, and the master out and slave in will be sent to the first slave, and the data out from the slave is sent to the data in of the next slave, and the data out from the second one will be sent to the data in of the other one, and the nth number of the final slave at the edge has its data out that is connected back to the data in of the master. So it is like a shifting the bits or the data sent to like a polling, right? So first whatever the data will be sent to this guy, and this guy will pass that data to this guy, and then this guy receive that data, and finally it will send that data back to the master. So all you need to do is chip select, enable all these devices, and start your clock and send the data. So whatever the data is available, let's say like this guy wants to send some data, so you still need to send data to this guy, and this guy receive, and whatever the data that this guy wants to send, it will send to this guy, and that data will be passed back to the master. So in that case, even though you have less chip select pins on the master, but that comes with some kind of compromisation, which is that you have to compromise your speed of your communication. For example, now you have to wait until all the data goes up to this guy and comes back to the master. So it takes more and more clock periods, right? So which means this one is much slower compared to the regular SPI mode, even though you're having a single chip select pin, right? But since we are running at megahertz range clocks, so the speed won't be a problem. When the application which is having less pins on the master, in that case you can compromise your speed and use this protocol, the SGN SPI mode, but that will be slightly complicated compared to the regular SPI mode, but still it's another type of SPI. Now I'm going to discuss a real-world application of SPI using MCP 3204 analog to digital converter, and how to interface it with the microcontroller. Actually, I'm not going to talk about much with the communication between the using a microcontroller. Instead, I will explain how this the peripheral can be used for SPI communication. What type of settings do you have to do? So MCP 3204 is a 4-channel 12-bit analog to digital converter. We know like most of the AVR microcontrollers that we have been using for our applications has 10-bit ADC resolution. But if you want more and more accuracy, this is one example. Like you can select 12-bit ADC analog to digital conversion if you use this MCP 3204 chip. So it is 4 channels. So there are 4 channels available for analog to digital conversion. And there's another version called 3208, which has 8 channels. But today I'm going to discuss only 4-channel device, which is MCP 3204. So these are the 4 channels: CH0, CH1, CH2, and CH3, like ADC node, ADC1 at megachips. And it has on-chip sample and hold, so the sampling and holding will be done inside the this device. So SPI is the communication method that if you want to get your ADC readings back to your microcontroller, so it supports the mode 00 and 11. You can operate this chip from a battery or any DC supply from 2.7 to 5.5. 5.5 is the maximum voltage that you can apply to the VDD of this device. And the sampling rate is 100 kilosamples per second when your supply voltage is at 5. Now these are the pin description. You can see these are the 4 channels, and NC means you don't need to connect these pin 5 and 6 to anywhere. Digital ground is for VDD, so you can connect the battery if you're having a battery power supply like 5-volt supply. You can connect this plus to this one and 0 to the ground, and this could be grounded to this one. When analog reference, you have to provide a reference voltage externally to this device. So based on your analog reference voltage, the ADC value will be determined. And if you use a external supply like a battery supply, let's say you provide a battery supply with 0.096 volts. So that is this connected to this ground. So at one point you have to combine this analog ground and digital ground, right? Otherwise it won't work. And finally you have this SPI pins, which is for your communication clock, data out, data in, and chip select. So internally, so it has a A to D converter, so which is same as the A to D converter in a microcontroller, and VSS is the ground or the ground pin, and VDE is a positive supply. And these are the, when you read the data sheet, these are the absolute maximum ratings, which means you should not go beyond than these values. Then you cannot use your device no longer, right? The device will be failed. So maximum voltage supply that you can apply to VDD is 7 volts. And when you're providing signals from external device, clock and the in nodes like that, so you have to keep this voltages not go below than minus 0.6 and not go over than VDD plus 0.6. For example, now if your VDD is 5 volt, so if you apply from a AVR microcontroller, so your clock voltage should not go beyond 5 plus 0.6, which is like a 5.6 is the maximum voltage that should be applied to this pin, and the lowest voltage should be minus 0.6, right? Minus voltages are possible like when you command these grounds, like when you command these grounds, there could be voltage drop in these lines, and the grounds are not same as this one, right? So in that case, there could be some negative voltages applying, but make sure you use short wires and never go your signals below than minus 0.6. Otherwise, the device will fail. And this device will output a digital out like a data, which is the ADC sample data. That data, binary data, is given from this equation. That is 4096 into V in. V in is your whatever the voltage that you apply to the ADC channel, divided by the reference voltage. The reference voltage that you provide to this thing, right? So depending upon that, you can get the binary value of the ADC readings from here. So this slide shows the typical input pin of this ADC channel of this device. So here, this is your voltage input. So the analog signal comes to this channel, like it could be channel 0, 1, 2, up to 3. So whatever this voltage signal, it should comes with the voltage source and the serial impedance. So even if you connect like a resistor divider, right? So we use resistor dividers, ground. So this could be connected to a battery, right? And R1 and R2. And this pin you couple to, let's say like this is VC to a ADC node or channel node. So by looking at from this point, looking at from this point. So it should be equivalent to a voltage source and a series impedance. So like for any AC signals, you can short circuit this voltage source, right? So that should be equivalent to something like the parallel impedance, like R1 parallel R2 of impedance that is shown to this point, and this voltage, right? So whatever the voltage, depending on the ratio. So that is RSS is, I'm talking about this simple example, right? If you're having a voltage divider R1 and R2, RSS, this series impedance is R1 parallel R2, like, like when you're taking small signals, you can just short circuit this AC voltage source, and the impedance is R1 parallel R2, and VA is the voltage that is available from this pin, like that is R2 into VCC divided by R1 plus R2. So whatever the voltage that you apply to any analog channel is equivalent to a voltage source and a series impedance. So inside this pin, like so it has like a parasitic capacitance which is in the range of 7 picofarad, and it has two safe diodes, like 2 diodes to protect this pin from over voltages. Now let's say like in absolute maximum ratings, I have shown you like this voltage should not go below than 0.6 volt, minus 0.6 volt, right? Should not go below than that. And also it should not go beyond that VDD plus 0.6, right? So that's because like these safety diodes can protect your pin from any voltages within this range. If it is go beyond that, it can protect to some extent, but cannot be guaranteed. Now let's say, let's think about this this point, like if you have minus 0.6, any voltage below than that, applying on this pin, right? VA. So if you provide a negative voltage, this is the ground, right? So since this is at low voltage compared to ground, this diode will be forward biased and the current will flow from the ground through this diode to this point and to your voltage source and comes back, right? When you're applying a negative voltage. So like a voltage drop across a typical silicon diode will be between like any generic diode will be between 0.3 to 0.7. So they shown like this is voltage is around 0.6. So there's a voltage drop that is 0.6. So this is 0 and minus 0.6 will be, this point will be minus 0.6 volt, right? That is because there is a voltage drop across the diodes, and the diode will keep, even if you decrease this voltage to -1, still the diode can keep this pin voltage to 0.6. That is, this voltage is constant to diode. The rest of the voltage will be dropped across this series impedance, right? Minus 0.4 volt will be dropped across the this impedance, PCB traces, and also the across this series impedance. So that's how this diode save this ADC channel from negative voltages. But if you apply any voltage over than VDD, right? Let's say if you apply 6 volt, now this is 6 volt, and this is if your VDD is 5 volt. Now like this voltage has highest potential, so it will keep conducting in this way, right? And since this is 5 volt and this is 6 volt, so there's a drop across this diode. So that is keeping this voltage always below than 0.6. Now let's say like this voltage VA is 6 volt now, right? And in that case, you can think about like you apply 6 volt accidentally, which is over than your VCC is, assume it is as 5 volt. So you know like this is again connected to a battery, which is connected to the ground. Okay. And 6 volt is higher than 5 volt, so definitely the current will flow from this part to the 5 volt line and to this charge this battery and return back to the ground. And this is also ground, so they are connected together, and it makes a circuit completed. So as this is 5 volt, so there's a voltage drop across the diode. They say like it is 0.6. So this point voltage will be 5.6, right? And 5.6 volt, and the rest of the points 4 volt will be dropped across this impedance together with the series source impedance and the PCB traces and this pin internal impedance. So that's how it save like no matter whatever the voltage that you apply, it will like you can apply up to 7 volt as the absolute maximum rating. This voltage at this pin will be kept VCC VDD plus 0.6. Right? If it is 5 volt, it is 0.56. Since this is diode will conduct when you apply over voltage, positive over voltage case, this diode will conduct and safeguard this pin. And there could be some leakage leakage current that is very low, like nano ampere range. And this is the ADC sampling and holding hold capacitor. And it has a series resistance of 1 kilo ohm, and this is the switch. So I'm not going to discuss about sampling and hold, which was covered in our ADC lectures. And so ADC conversion takes sampling takes at least 1.5 clock periods. Like this is a complete clock, right? And this is another clock. Let's say this is clock number 1. This period is clock number 1, and this period is clock number 2. And in order to make sampling and holding, it takes 1.5 clock cycles, which means from this point to this point, right? This is the 2 complete clocks, so it takes time between from here to here. It is 1.5 clocks. And in order to get the fully conversion done, which means like you have to request the data, and this one will transfer the data using 12 bits. So in order to send your ADC readings as a 12 bit, it needs 12 clock pulses to transfer this 12 bits. And we know like clock has to have a frequency. So the clock frequency should be selected based on your input resistance, right? So it's input impedance. So otherwise there could be some problems with your ADC readings. So if you use VDD as 5 volts, so your supply voltage is 5 volt, you can use 2 megahertz clock frequency when your impedance is source impedance is less than 1K, right? I have shown you how to calculate the source impedance. If you use like a battery connected here with connected to this pin, like let's say you use 1.5 battery connected to this ADC pin. So battery has an internal resistance, so that will be your internal resistance, right? So that is very low. So you can use 2 megahertz. But if you use something like a resistor divider, let's say you use 2 10K resistors and make like a resistor divider and get this voltage from here, and here you connect to VDD. So the impedance of this seen from here is the parallel impedance, like 10K parallel to 10K is 5K, right? So somewhere here, 2, 3. So this is on log scale, right? This is 100 ohms and 200. Likewise, this is 1000, 2000, 3000, 4000, and 5000. So we have to go to 5000. And so you have to use a clock frequency below than this. This is around like 1.7 or something, but use of 1.5 megahertz will be safe. If you're using more and more higher impedances, so you have to use slow and slow clock rates, right? That is due to this charge of this capacitance through this series impedance. So it takes some time because ADC conversion takes 1.5 clock cycles. So if you use higher and higher clock speed, if you increase this resistance and in order to charge this capacitance as this sample capacitor, charging this capacitance takes some time. So as you increase the impedance, you have to definitely slow down your clock speed. Otherwise, these capacitors will not be charged to the particular voltage that is appearing in VA. It takes some time. So, like RC time constant, in order to charge a capacitor via a resistor, it takes some time, right? So it has to be given some finite time to charge these capacitors. If you have use a very high impedance, like 100K voltage dividers and like that, you cannot use very fast clock period because 1.5 clock period is not sufficient to charge this capacitor to whatever the voltage that you provide from your source, right? So let's say your analog voltage changes from 0 volt to 1.5 volt, but still this capacitor is not charged to 1.5. It may be it's still around 1.2 volts, right? But you have already passed 1.5 clock periods, but your ADC readings will be 0.2, but you expect 1.5 volt. But due to this impedance mismatch, impedance RC time constant, your capacitors are not charged to the real voltage appearing at this your source at that time, right? That's why you have to slow down your clock speed when you're using a high impedance input impedance at your source side. So that is you have to follow this graph if you want to select the right clock speed in order to get the correct ADC reading from this device. Now this is the SPI timing of this device. So initially the clock select is at logic high. You have to pull this line to initiate the data transfer, and the clock could be either logic low depending upon the SPI mode or logic high, and you have to generate the clock pulses, and you have to provide the digital data out from the master, and then you will receive the data from the this ADC converter. So initially it will send a null bit which is 0, and then it will start sending the all 12 bits which is corresponding to the 12-bit ADC conversion. And most significant bit of your ADC conversion will send first. Now you can see the data format of this SPI communication. So if you want to start a communication, you have to pull this CS bar line down. So this is where you start the communication. And then you have to send clock pulses. So this chip select and clock pulses will be generated by this master, typically a microcontroller. And then you have to send this data out from the master to the slave. This is received by the slave. So you have to send 5 bits to initiate, which is readable for the slave, right? First is the start bit, so you have to whatever this be in line with the high or low when you pull it down. So you have to set this bit to high. So this should be high, right? Start bit is high. Then you have to tell this device to send it as a single or differential mode. Single mode means you just use a single channel. If you use differential mode, so it is like a subtraction of like channel, two channels, CH0 and CH1. So the output will be CH voltage applied to CH node minus CH1 will be the differential voltage if you select differential mode, right? But most common way is selecting the single conversion, which means you just select one single channel. And so this is one, and if you use a single conversion, this should be one, and then you have to tell which channel that you want to get done the ADC conversion. If it is channel 0, so D1 and D node should be 0, and D2 is don't care. Either you can put it as 1 or 0, it doesn't matter, right? And if you want to send, for example, now channel 3, this could be D1 and D node should be 1. This could be either 0 or 1. You can keep it as 1 as well. So if you want to get the ADC reading from channel 3, all you need to send 3 files from this line when you pull the CS bar down, right? So that will be understood by the slave. Then the slave will start sampling. So it takes, as I mentioned, 1.5 clock pulses. Here we have seen 1.5 clock pulses. So this is that. You can now see this is the starting point, and this is a 1 clock period, and this is half of the clock period, and it will start sending the data from the slave, the ADC sample data as a 12-bit number, right? This is 12-bit. This is bit 0 and this is bit 11. Altogether, it is 12-bit, and it will send a null bit at the start, right? From the slave. This is always 0, and then you have your 12 bits followed by this 0. So you have to keep providing this clock pulses until this last bit is sent from the slave. Then you can deselect the chip, which means you can set this line high. So then the communication will be terminated. And again, if you want to get another sample data, again, you have to pull the line down and send whatever the channel you want to have, and this data bit. So then it will start sending a next data packet from this line. Right. Now we can have one simulation example. You can see now I have used MCP3204, and I'm using a ARF as a battery 0.096. This is my reference voltage, and this battery could be replaced with like a real world device like analog reference. MCP1541, if you use this device, you can replace this battery and put this device, right? That is the recommended. In real world, you can have like a 0.0996 battery. Instead, you can use this device and connect it to a 5-volt supply, and then it will output a 0.096, right? And I have connected the voltage divider on channel 3, which is connected to this reference voltage, which is half of the reference voltage will be available on channel 3. Close to like 2.048 volts will be available on channel 3. And without writing a code and using a AVR microcontroller, what I did was I have used pulse generators on these 3 pins. So I have used a clock generator for clock pin, and D in also I have used a pulse generator to generate the particular bit pattern that I want to select the channel. And for chip select also I have used a pulse, and then this device will output the particular data packet out from this dout pin. So when I run this, so I have received this kind of data packet. So let's take what kind of data that we have to get from the device. So digital output call from the device is given by this equation. It is available on the datasheet. 4096 into V in divided by Vref. V in is the voltage applied to channel 3. That is half of the this reference voltage. Vref divided by 2. And divided by Vref is simply 1096 divided by 2. Right? That should be 2048 in decimal. But if you convert to a binary, that is 1 and 11 zeros, right? 2048 in binary is 1 and 11 zeros. So when I simulate this, like I have selected channel 3, so my D in should be 5 months according to the datasheet, and I should get D out as 1 and 11 zeros, right? So this is chip select. So I have initially it is high, and I have pulled this line down, and where this is starting the conversion, and then clock pulses will be generated by this clock pulse generator. And you can see now, so this is 1 clock period, and this is other period, and 3, 4, 5, right? During all this period, D in should be high, right? So it should be 5. So 1, 1, 1, 1, and 1. So 5 ones. So this is the data packet I'm sending from the microcontroller or my signal generator to the device. So it is asking from the device, send me the ADC sampled value applied to channel 3. So this is the start bit, and this is the whether the conversion is single-ended or differential. So single-ended is 1, and this is don't care bit. I have kept this as 1, and to select channel 1, these final 2 bits should be 1. And the middle of this last bit of the D in channel, so it takes 1.5 clock period to sample and get ready the data. So that is that period. At the end of this period, so it is starting with this null bit, which is 0, and then it is every clock period falling edge, it is sending data. And so you can count this clock period. So this is a 1 clock period, and this is 1, and this is 0. Likewise, all together up to this point, it will be 11 zeros. So that is this number, right? And again, I have deselect my chip from that signal generator. This is the pulse that I have generated, considering the timing. So in that case, I have kept the clock frequency as selecting to a value depending on the datasheet specifications, save value, following this one. So I have used 2 10K resistors, so that is around like 5K, right? So impedance, the RS value here, since I'm using 2 10K resistors, it should be 5K. In that case, I have to select my input supply is 5 volts. So 5K is 2,000, 3,000, 4,000, and 5,000. So I should use a clock frequency less than 1.6 megahertz. So I have used, I think, 500K as my clock period. So this is clock period frequency is 500K. And kilohertz frequency. So then it has sent this data packet, and when I convert it back to it is 2048. So this data packet 1 and 11 zeros is corresponded to 2048, which is the value that I want to get from my ADC. So all are working fine. So then I can use it for any other purposes. If I want to select this different channel, I can change this bit pattern on the in and get the data to other pattern, or even I can change this resistor divider values and get the corresponding ADC reading from this D out pin. So that's all about the SPI communication. So I have explained you how to use this ADC. I have explained you how to use this MCP3204 ADC converter, and how to get the ADC reading. So I would like to give you this problem. So in that case, you have to write a code in Atmel Studio using Atmega 16 microcontroller to receive the data from multiple channels of this MCP3204 analog to digital converter using generic digital pins. Do not use the SPI dedicated hardware. Instead, you can write a code to manipulate whatever the bit sequences that I have generated using delays like that. And you can test your code and verify using a suitable simulation package. So what you can do is like you can connect this device to this. You can see like I have used signal generators. Instead, you can connect it to a microcontroller, and you can generate these waveforms by using delays, right? So if you use chip select, initially you can set that pin to high, and if you want to start the communication, you can set that pin to low. And using delays and with the right frequency, you can set this the other clock pin to low and high likewise. And during this period, the in could be set to high or low depending upon the input channel and whether it is differential or single ended. So you can write a code using while and for loops, and then the device will output the digital value. Then you can copy that value to a 8-bit number, two 8-bit numbers, and convert to a decimal value, and you can display in Atmel Studio itself, or copy to another channel of your microcontroller. You can just copy it to a LCD screen or 7 segments or whatever desired. So I'm giving this problem to solve by you. Try to write a code without using SPI dedicated hardware. Just use a generic 4 digital pins and start with this bit sequence. And if you can observe the output from the device as this kind of bit sequence, you know your code is working. Then you can change the channels. So you can use some sort of channel selection. Either you can make a delay and rotate the channels, like channel 1 first and get the conversion done, then the channel 2 and likewise. Or you can use like a switches to select the channel using using another digital pins. Like if this switch is pressed on this digital pin, channel 1 should be sampled, and SPI signals for the in should be sent for that particular channel selection. Likewise, you can think about different configurations and solutions, right? All I'm expecting is write a code to manipulate this bit sequence depending on the channel selection. You should get the right value for the right voltage that you apply here. So that concludes the SPI communication protocols, and I hope this was useful for you to understand what is serial peripheral interface and how to connect external peripherals like this ADC converter, and how to get the data and how to read the data correctly. And writing the code for that, I am giving you as a problem. So you can right, and you can test it using a simulation package. So you can verify if it is working properly. You can back calculate and see whatever the data that you receive is the one that you expect from theoretically, right? You know this voltage and you know what should be the converted value, and you know what kind of data you should receive. And in that case, you can verify your code. So that concludes this lecture, and thank you.